Hi there, I'm John Brackins, a doctoral candidate at Tennessee Tech University in Civil and Environmental Engineering. My project title is Evaluation of Tropical Cyclone Flood Discharges Estimated with Rainfall from Parametric Models for Flood Risk Studies. Let's dive on into the poster. So I'm not going to read the abstract to you, but I will summarize by saying that we're looking at tropical cyclones and the rainfall produced by those, and if we can use statistical parametric models to effectively determine TC flood discharges using the rainfall that we would get from those models. Previous work by myself and Dr. Kalyanapu has demonstrated that the IPET model that we'll talk about was the most skillful in this area of the four that we evaluated. These tropical cyclone maxima affect all of FEMA Region 4 at greater than 1,000-year ARI, with the exception of Kentucky. TC rainfall events then have the potential to affect the tail of flood risk statistical distributions. And so we need to be able to simulate those from a joint distribution of parameters that govern tropical cyclone behavior, the track, size, and intensity. 4 existing parametric models already attempt to predict rainfall patterns from these variables. Those are the models that were evaluated in Brackins and Kalyanapu 2020. And they simplify the very complex structure of tropical cyclone rainfall into much simpler methods. So the research objective today is to perform a case study using a HEC HMS model of the Shenandoah River to determine if rainfall produced by these 4 parametric TC rainfall models allows for sufficient representation of TC flood discharge. We're only going to look at one of them today for space and time considerations. So the 4 that were ultimately considered are RCLIPER, IPET, FRAM, and PCLIPER. A little bit more on each of those. RCLIPER is essentially the climatological mean rain rate from NASA TRMM satellite data for tropical cyclones from 1998 to 2002. IPET is a similarly coarse model trained on similar data that incorporates storm size and some asymmetry by multiplying rainfall rates on the right-hand side of the track by 1.5. FRAM modifies the symmetric RCLIPER using wind shear and topographic effects. Wind shear has the power to redistribute rainfall, but it can't change the overall amount of rainfall, whereas orographic effects can cause more rainfall to occur. We didn't include wind shear because we're working in Western North Carolina, where orographic effects are expected to be more important. PCLIPER is the 4th model that we're working with, which is probability distribution functions, again, based on TRMM and a frequency tuning knob that allows us to turn the rain rates up and down. So the HMS model that we were working with is from a FEMA effective flood study. It was a 133 square mile watershed of the Shenandoah River that uses Muskingum-Coons routing with an 8-point cross-sectional representation, 35 subbasins, half of those roughly as Green and Amped and half as SES curve number, depending on imperviousness, and Snyder unit hydrographs used to transform hydrographs during routing. So setting geographically where we are, the Shenandoah River, which is a tributary of the French Broad, and we have several precipitation gauges in this area historically, as well as 3 USGS gauges. We're going to look at output at this Shenandoah River gauge station today. So the HMS model includes 2 reservoirs, one that's about 10 times as large as the other one. And again, we're routing that flow down these 8-point cross-sectional representations. We looked at 2004 hurricanes Francis and Ivan, 2 storms within September 2004 that came to this area and followed similar tracks. So we compared the parametric rainfall model IPET with multiple sources of observed data. We had the NLDAS data, the historical gauge at Asheville, North Carolina, and a stage 4 QPE for this area as well. So there's some variation evident in that observed data, even at the same location. And we'll go on to see that the IPET model does not produce sufficient rainfall to reproduce peak discharges. Looking at how it actually performs, we have our historical gauge, our NLDAS, our stage 4, that follows similar temporal trends as well as similar total rainfall amounts, whereas IPET falls short in both of these categories, both with the timing being slightly off and the amount being very far off, such that the routed hydrographs have much smaller peak discharges. Unfortunately, that means that these parametric models are likely insufficient for modeling TC flood discharges. And I would like to acknowledge NSF. Thank you.